Here's the study guide for chapters 19 through 22. We're going to have a Zoom on this in a couple of days, and if you have any questions, please either email me or we can discuss them at the Zoom before the exam as well. All this information can be found in your lecture notes, but we're going to go over it one by one as a nice summary. So this is going to be your primary resource for the exams. So I'll try to remind you of many of the references as we come to them as we go through this. So the first one, know how acids and bases are similar and how they're different with flavor and dyes. First of all, acids. Acids tend to be like lemons, okay? Lemons are going to give you some type of sour flavor. Bases are a little bit different than acids. And if you tasted baking soda, go ahead and taste baking soda at home if you'd like. A very small sample. It's not sour, but it's bitter. So those are two different flavors. They're stimulating two different taste buds on your tongue. And how they are, so that's how they're different with flavor, but they are similar with their dyes. And in both cases, it's a big concept in chemistry that we really didn't get to emphasize as much as previous years. But when you change the acidity, or if you change the pH, what happens is you change the shape of the molecule. And sort of like every bone in your body has a different shape and it has a different function, with molecules it's the same way. If you change the shape, you're going to change the functionality of that molecule. And if you change the shape, you're going to be changing the color of that molecule as well. So how they're similar, they're similar in that they're both like this with the, when they change their shape, they're going to be changing their color, and they're different with their flavors. Names and structures of two ions produced when the molecules bump into each other. So if you have two waters, H2O and H2O, when these bump into each other, they form the H3O plus. One of the hydrogens gets transferred to the other one. So if you can imagine taking an H off of the H2O here and adding it to here, you get H3O plus. And if you've taken an H off, you're left with an OH minus. So the H3O plus is called the hydronium ion. And the OH minus is called the hydroxide ion. Know the atom on acids. To identify acids, you're going to be looking for an H, particularly an H+. And bases, how to identify them? You identify them with OH minuses. So the hydroxide is a good example of a base. Note the definition of neutral. Neutral is with these concentrations. Now if you remember, concentration has the symbol with the brackets like this. So your hydrogen concentration and your hydroxide concentrations, when it's neutral, when you're at neutral, you're at a pH of 7. You're in the middle of that pH scale. And these two concentrations are going to be equal. We talked about how a lot of people have this misconception of neutral being neither acid nor basic, but it's actually both. It's an equal concentration of both acids and bases. Because if you're taking two water particles which are neutral and they bump into each other, you produce one, which is the hydroxide, which is the basic, and the hydronium ion contains the extra H+, which is the acid. You get one of these, you get one of these, and so you have an equal concentration of both. So when you're acidic, your pH is going to be less than 7. And when you're acidic, you have more acid than bases. Basic is when your pH is greater than 7. And that's when your OH concentration is going to be larger. So identify the pH of a solution according to the molarity of the H plus concentration. I'm going to give you a couple examples. There's a formula that we had from our lecture notes, and it's the negative log of the molarity concentration, but there's an easier way to do this. If you have a concentration of 1 times 10 to the minus 5 molar of H plus, this is going to be giving you the pH of 5. So the pH is your exponent there. Okay. If you are given the 0.0001 molarity of your H plus concentration, you need to convert this into scientific notation. So this would be 1 times 10 to the minus 4, which means that this would give you a pH of 4. Going in reverse, identify the concentration of H plus from your pH. So if you have a pH of 12, we're working backwards now. And so your H plus concentration will equal 1 times 10 to the minus 12 molar of your H plus. So in this case, kind of working backwards. So draw the pH scale. What is acidic and what is neutral and what is basic? So your pH scale ranges between 0 and 14. In the middle is 7, and 7 is going to be your neutral. Anything between 0 and 7, you're going to be acidic. Anything between 7 and 14, you will be basic. And again, when you have an acid, you have an H plus concentration. And when you're basic, you have an OH minus concentration. Compare HCl and acetic acid. Describe why HCl is the stronger acid. We did a lab on the battle of the acids. And it's because if you have an equal number of molecules of HCl and an equal number of molecules of acetic acid, about 90% of the acetic acid molecules will stay as acetic acid, and they will not fall apart to produce the H. So with the HCl, what we get is we get 100% what's called ionization. We get 100% ionization, which means that 100% of it, all molecules, this all falls apart to H plus and Cl minus. With acetic acid, you might get something like 10% ionization. Very few of the molecules fall apart to produce the H plus molecule. So with the hydrochloric acid, we get lots of H plus molecules. And if you have lots of H plus, that's going to make it more acidic. That's going to decrease the pH. If you have very little ionization, you're just going to have very few acid molecules. It's the same thing with sodium hydroxide and ammonia. With the sodium hydroxide, you get 100% ionization. And because of that, we get lots of the OH minus molecules. With NH3, NH3 reacts with water to produce the hydroxide ion, but very similar to the acetic acid, you get very few molecules that will actually fall apart. You only get 10% ionization. So you get fewer of those basic molecules. How to neutralize an acid or a base in the direction the pH will be shifting. So if you're on your pH scale, between 0 and 14, we're trying to neutralize something. So if you're trying to neutralize it, you're trying to get it to 7. So if you have something of like a pH 14, or right here, what are you going to do to get it to be neutral? You're going to add an acid. And if you add an acid, it's going to shift it in this direction. Similarly, if you're over here, you're very acidic. How do you neutralize an acid? You add a base. It's going to shift it towards being neutral. Know what a salt consists of, and how to make a salt by knowing which acid to add to which base. So if you remember a salt, this is produced from a neutralization reaction. So with a neutralization reaction, if you remember, we get the products of water, and we get our salt, which is some type of ionic compound with a positive ion and a negative ion. Let's do, for example, aluminum chloride, AlCl3. Well, if you remember, these molecules are going to fall apart. And let's take a look at this water will also fall apart if we're working backwards to try to recreate this. So we have an acid. Acids begin with H+. So I have a molecule that has an H+, and a base is going to end with an OH-. Remember, ionic compounds or compounds always begin with pluses and they end with minuses like this. So of my AlCl3, I can do the reverse crisscross. Okay, this will show me that Al is a 3+ and Cl is going to be a minus. So where's my Al going to combine with? Is it going to combine with my H, or is it going to combine with the OH-? The positive ion can't interact with the positive ion because it's going to get repelled. So the positive ion reacts with the negative ion. Okay? So I can do the crisscross now, and this will show me that I'm going to have 3 of those OH minuses to counter the positive 3 charge on that. And the H is going to react with the Cl. The charge on the Cl is minus. Let's try to balance this. And if we take a look, we have 3 chlorines here. We're going to need to have 3 chlorines here as well. 3 times 1 is 3. That gives me 3 H's and gives me 3 OH's. That will give me 3 H2O's. So on to the next, balance an acid-base reaction. So I'm going to give a very similar reaction, and it's going to be magnesium hydroxide, MgOH2, plus HCl. So we're adding our base. Oh, that was not right. Sorry. The 2 is on the outside. And we have hydrochloric acid. And we can see what's going to be produced from this. The Mg will be positive. It's not going to react to the positive. It's going to react to the negative. So we're going to be forming magnesium chloride, MgCl2. We're just going to be balancing this. And we're also going to be getting waters. How many waters am I going to get from this? Well, let's try to balance this. I have 1 Mg, I have 1 Mg. I have 2 Cls, therefore I'm going to have 2 Cls here. Here I have 2 H's and 2 OH's. 2 H's and 2 OH. If you remember, H and OH adds to water, it's going to be producing 2 over there. We also had a buffer lab, and this is when we added hydrochloric acid, and we saw a rapid change because there was no buffer present. But if you put a buffer in, it took about 30 to 40 drops to get to the same pH when adding acid. So a buffer, it doesn't stop the pH. The key word to this is it's going to resist the pH change. So that's the first chapter on acids and bases. So the next chapter is looking at redox reactions and also electrochemistry. So the definition of electricity is when electrons flow, or it's the flow of electrons. What's happening to electrons during an oxidation reaction and reduction reaction? Remember, this is the pitcher, and this is the catcher. It's called a redox reaction, but the oxidation is going to be taking place first. So here's the oxidation. It's the first one. The reduction reaction is the second reaction. So here's the pitcher. Here's the catcher. So it's the electron. The electron is the ball. The pitcher is throwing the ball to the catcher. So the pitcher is going to lose the ball or lose the electron. The catcher is going to gain the ball or gain that electron. Know the significance of the redox reactions. Again, we have this redox reaction. The reduction takes place second. The oxidation takes place first. And the electron has to have a place to go. It just can't go out into space. So the electron is being passed. The electron is being passed. It needs a place to go. It goes from the higher level to the lower level. So it's passed. It needs a place to go. So that's why we have to have a pitcher. We also have to have a catcher. Looking at voltaic cells, how the chemicals are used to create electricity. So we have a zinc strip, we have a copper strip. If you remember, the zinc is going to be in your solid form, this is going to be neutrally charged, and it has the higher activity. It's higher on the activity chart. And when connected to a system next to copper ions, it's going to transfer its electrons to those copper ions. So the zinc will fall apart and it will become charged, and it's going to be giving up the 2 electrons. So the zinc is going to dissolve. This becomes now aqueous or dissolved and produces those electrons. Those electrons then transfer over through the wire to a copper ion, and it will do so because this is a lower activity, this is a higher activity. It's sort of like building up pressure. It's going to release that pressure by giving it. And when the 2 electrons, the 2 negatives combine with the 2 positives, this will produce solid copper. And these are the deposits that we get on the electrode. We'll draw all this as a quick summary as well. Know what an electrode is? An electrode is usually some type of metal, like the zinc or the copper, and it's a metal conductor. Difference between the anode, look for the N in the anode. The anode is the negative electrode. The cathode, that looks like a positive with the T, it's the positive electrode. What happens to the mass of the anode and the cathode, and whether they're shrinking or growing in a voltaic cell? The anode is going to be the negative. This is the source of the electrons. This is the pitcher. So I'm trying to keep all these things on the same side. So it's the pitcher losing the electrons. It's the negative electrode. What's going to be happening to it? The negative electrode is going to be doing this reaction over here. It's going to be dissolving. So the anode, or the negative electrode, is going to be decreasing in mass. The cathode is going to be growing in mass because the electrons are going to be transported over to the dissolved ions. The dissolved ions will then absorb those electrons and become solid deposits. What direction do electrons travel? They travel from anode to cathode, from the negative towards the positive. Where is oxidation taking place? This is taking place at the anode. Reduction is taking place at the cathode. So let's go ahead and draw this voltaic cell here with the two sides of the voltaic cell. Okay, we're just going to sketch this. We'll leave some of the details out. Okay, over here we have the zinc, and over here we have the copper. The zinc is going to dissolve. Okay, so it's going to dissolve into this, and it's going to give the two electrons. The two electrons will then go into the copper electrode. And what we do is we have copper that's sitting here, which will see those electrons, and then they will bind onto them once they're passed onto the metal. That's this reaction right here. The zinc dissolves, producing the two electrons. The two electrons combine with the copper to produce the solid deposits. So we get deposits that are going to get built up over on this end over here. So because of this, this is going to lose mass. This is going to gain mass. This is the negative side. This is the positive side. Oxidation occurs over here. It's the pitcher. Reduction occurs over here. This is the negative, so it's the anode. This is the positive, so it's the cathode. So that's the voltaic cell. So know how dry cells differ from traditional voltaic cells. When I talk about dry cells are going to be your common battery. Your common battery. And I'm talking about your AAA, your AA, your C, your D cell batteries. Okay. How dry cells differ from traditional voltaic cells? Well, voltaic cells, if you remember from here, these have liquids. This is like the lab that we did with the dialysis tubing and the blue liquid on the inside of that. Your common battery or your dry cell has this paste. It's an electrolyte paste. So your dry cells have an electrolyte paste instead of having these solutions like this. Common battery has electrolyte paste, okay, and instead of liquids. How does an alkaline battery differ from a common dry cell battery? So an alkaline battery is a dry cell battery, and a common battery is a dry cell battery. Alkaline batteries have a different substance in their electrolyte paste. They use a base called potassium hydroxide. So they use the base, which is KOH, in their paste. In the paste that they have. So because of that, they don't produce this ammonia gas. So in a common battery, the electrolyte paste is going to have this ammonium ion in it. Okay, this is going to be your common dry cell. And what happens is, if you remember the ammonium ion, this becomes your electron receptor. This becomes your ammonia gas, which is NH3. So here's your ammonia. This builds up pressure on the inside of your battery and can cause it to leak or explode. So if we have potassium hydroxide in the paste, we don't get any ammonia gas. So since there's no ammonia gas, that means the alkaline battery is going to last longer. Which lasts longer? The alkaline one lasts longer because no ammonia gas, which means that there's going to be less leaking. It's not going to guarantee that it's not going to leak. It just means that you're going to have less leaking because of that. Okay, next one, and this is going to be the last page. Know the number of bonds that carbon is able to form. Carbon is able to form 4 bonds like this, 1, 2, 3, 4. Know the function of hydrocarbons and the atoms that compose them. So let's talk about the atoms that compose them. The atoms that compose hydrocarbons are going to be hydrogen and carbon. What's the function? Well, hydrocarbons, you burn them inside of your engine. We also eat hydrocarbons, such as fats or oils. We'll get to this in the next chapter. So the function for hydrocarbons is we can have them being fuel for our vehicles, or they provide us with energy. They also can provide heat in both cases because they heat the engine, they also heat our bodies. So you need to know the parent names, methane through octane. So if remember, we got 1, 2, 3, 4, 5, 6, 7, 8. This is going to be your MePB. And after that, they take on the names for the shapes of polygons. This is going to be a pentagon. This is going to be a hexagon. 7 is going to be hept. 8 is going to be oct. Okay, your first one's going to be methane, ethane, propane, and butane. If they could be single bonds, they could be double bonds as well. Know the parent names. Know how to name and number linear branched alkanes. Okay, so here is going to be an example. You're not going to have to draw them on the test, but you will have to name them. So let me go ahead and give you an example. Draw 5 carbons going across. Carbons on these 2. Carbon like this. So the longest one's going to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, so we're just going to do this as being the longest, parent. So because it's a 5 carbon, it's going to be pentane, and it's an alkane. Okay, alkanes are going to be ones that have single bonds. We'll get to alkenes in a little bit, which have double bonds. Alkynes are going to be your ones with triple bonds. So how do you name this? This is a 5 carbon alkane, so it's going to be a pentane, but then we also have your side groups like this. This is going to be a methyl group, an ethyl group based upon these. Remember, your side groups end in YL, we have to put them alphabetical. Ethyl comes before methyl. So this is going to be 3-ethyl. Oh, actually, we have to number them. Our side chains, how do we number them? 1, 2, 3 this way or 1, 2, 3 this way? Well, if I number them this way, 1, 2, 3, my side chains become 3 and 4. If I number it this way, 1, 2, and 3, they become 2 and 3. So this is the first carbon, second carbon, third carbon, fourth carbon, and fifth carbon. Ethyl has to come alphabetically. We have to number our carbons in this orientation because it's going to be groups 2 and 3 versus groups 3 and 4 if I numbered them from this way. So it's 3-ethyl, and it's going to be 2, 3. How many methyls do I have? 2, so I have to have the prefix di. Dimethyl, and then I'm going to have dimethyl, and it's a 5-carbon pentane. Okay, so let's do one with an alkene. You can draw 4 carbons going across. 1, 2, 3, double bond 4. Do 2 carbons going up like this, and 2 carbons going down. Our rules are a little bit different for this. Our rules are that our parent has to have the double bond in it. So if I take a look, I have 1, 2, 3, 4. I have 4 with a double bond. I can try this way, 1, 2, 3, 4 with a double bond. 1, 2, 3, 4, 5 with a double bond. Well, why can't I do this? 1, 2, 3, 4, 5, 6. I can't make that because the parent doesn't have the double bond in it. So my parent is going to be this, and my side groups are going to be this and this. Here's my methyl, here's my ethyl. Now the rules are a little bit different because now I have to number my bonds according to which is going to have the lowest number. The double bond here will have a position of 1. If I started numbering from here, it'd have a position of 1, 2, 3, 4. So in ordering, you have to give preference to the double bond, which means the carbons are going to follow. Carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. So I've numbered everything, I've labeled everything, now I have to name it. So remember, we're going to be going alphabetically. So this is going to be 2-ethyl. Okay, the methyl is on a 3, so it's going to be 3-methyl. And it is going to be, it's an alkene, and it has 5 carbons, so it's going to be also a pent, but it's going to be pentene. But what number is the double bond attached to? And it's number 1, so it's going to be 1-pentene. Last concept is how to fractionate something. We're fractionating crude oil. And if you remember, this happens in the fractionation tower. Your crude oil comes in as this black, tarry liquid. And it's now in the liquid phase. And it goes up the tower. And then there are going to be areas where it's going to cool and condense. So this comes in as a liquid and is going to get heated. So this crude oil will become a gas. But as it gets further away from the heat source, it's going to cool back down into a liquid again, and then it will leave the fractionation tower. And it will do it at different levels. This is going to be the highest condensation point, lower condensation point, lower, and the lowest condensation point will be at the top. So the main concept of this, as we discussed, is that you heat your crude oil into a gas, just as we did here. It's then going to cool, and when it cools, it's going to condense. And of course, it's going to happen at different temperatures. Condense at different temperatures. That's it.